So hello everybody, it's nice to be here and share our experience with you guys who share the same passion for CubeSats. So I'm representing the Vilnius University team, currently holding the position of Research Fellow in Faculty of Mathematics and Informatics. And I would like to also thank the co-authors and contributors to this mission. Without them it would not be possible. So you can see some of them here in this picture. So I would like to start from our background story where we started. It's actually a fault of me and this guy who's sitting over there. So we actually had the dream to launch the first satellite for Lithuania. Lithuania is a small country which doesn't have its space program. Didn't have its space program at that time, about 4 years ago. So we said to ourselves, we don't care, we just want to launch this satellite. And I think that, as was pointed out during Thursday, that it's really the CubeSats enabled this private initiative, connecting people and opening opportunities for small countries to come to this space field. So we started as private citizens. We didn't have any state support, university support. We were just students. What we did is actually we tried to make public announcements, presentations where we pointed out the importance of space for economy, for policy of the country. And we actually founded a non-profit organization called Innovative Engineering Projects that was founded by me and my colleague. We had a chance to be at NASA Ames to do an internship for 3 months, and that's where we met the nanoracks. At that time, they were the only company who could actually provide launch from ISS, and that was really a very attractive opportunity for us because the time frame that they could put the satellite in orbit is very short, and really they do help with all the bureaucracy, so we don't have to deal directly with NASA, but basically do the commercial way by letting this paying for nanoracks actually. Then when we came back, we actually contacted many companies from Lithuania who contributed with any resources they had for this mission. So it was really a good selling point, the first satellite for the country. So, but of course, we also we understood it's very important from educational aspect. We want to really educate the new generation that would be capable to perform space projects in our country. So that's why we also involve people from university like Vilnius University, Vilnius Gediminas Technical University, and others. And what we found also is that the school children are also very important. That they are observing the situation, what is happening in the country, and if you want to have really a generation of motivated people that would not leave your country but actually contribute to it, you really have to show them example, and this is the space project, I think, is the best way to really to do that. So let's move to the technological side of our mission. Our payload was one of the payload was a FM voice repeater. We wanted to prove the feasibility of this repeater for CubeSat. As far as I know, if not, correct me, we were the first to put this type of transponder in the CubeSat. And the reason why we wanted to use FM is that we think it's more accessible for hams, and it is more suitable for STEM education for school children and students. And don't need really sophisticated equipment to do contacts through this type of transponder. And actually, I was able to close the link just standing in the forest with a handheld radio. So that was really impressive. So this is a dual band transponder. It's a VHF uplink, UHF downlink with about 150 milliwatts of RF power. The other payload was Cox camera. We decided that we want to use an imaging system that is basically running in Arduino, and we also were looking for the camera that had its onboard image processing capability, low mass and low power consumption. So we decided to stick to one camera model, although we upgraded it a bit. We put the aluminum housing, our own developed instead of plastic, and we also put some wide-angle lens on it. Then moving to our system design, basically we had a central hub, the main computer that was communicating with the EPS through I2C bus, and the communication system, and a secondary computer that was basically running the Arduino code on the Mega controller and controlled the FM beacon and the camera. We had to use the I2C because the GOM-Space EPS does not support any other bus. We think this is the downside of this product, although we are generally we are satisfied with the performance of it. Also, the positive thing about GOM-Space for this mission was that it uses the batteries that are has space heritage and are space qualified. And if you probably understand that if you want to put the payload in ISS, really NASA is very careful of what are you carrying there, and you don't want your batteries to explode in ISS. So in this respect, it was advantage for us. Then the FM transponder did not have any data exchange with other subsystem. It was fully independent. We just had to turn on the power through the EPS, that's all. We used the passive ADCS system with permanent magnets and hysteresis rods for passive magnetic stabilization. The communication system was also cast from USA, and it was using 19.6 AX25 protocols. The main controller for the flight computer was ARM-based, ARM Cortex-M4, which had various sensors that we wanted basically to compare the data from them. And then, of course, the solar panels, 6 on each side of the one new CubeSat. This is basically the view of the structure and antennas. So we had the aluminum sheet metal structure type. Basically, it is a little bit modified pumpkin frame that we used. We also had a sophisticated antenna design because we decided we won't use commutation. And since we had 3 transmitters, one from transponder, one from transceiver, one from beacon, and also 2 receivers, it was basically a very quite a harsh requirement for the antenna system, and we really did a lot of studies, and this configuration was actually the best we could get, but it still had really a lot of dips and nulls in its antenna pattern. We used the silicon solar cells on each side. It was in-house developed in Lithuania. The advantage was that they could basically cut individual cells to the shape we wanted. For disadvantage is that it's less efficiency is less than the triple junction cells, but because of the budget, we still had to stick to this option, limited budget requirements. So this is our schedule. We started summer 2012 with a concept that we actually developed during internship at NASA Ames. It took us about a year to finish the detailed design, and then it also the crazy thing started to appear. We had the limited funding, delay in funding, so the procurement for the subsystem was delayed, and we actually got the final hardware at about at the September of 2013, and we had to quickly integrate everything and do the tests. So that was really a crazy time for us, but we managed to escape somehow. And I think yesterday there was a discussion of how is it possible to do L-1 month with nanoracks. It's really possible to do even in less. Believe me or not, the launch contract was signed in September, so about 3 months before the launch. Of course, we were communicating with nanoracks before, but we think it's a great, the nanoracks and all this platform and ISS really provides a very quick time to orbit that may be used as an advantage for some projects. This was the launch that happened from ISS, and yeah, I would also say that one of the advantages of launching from ISS is having these nice pictures. But of course, then what we were interested, of course, is this, the results. So during fast orbit, we got the data that was pretty much okay, although there was a lot of fading due to spinning, initial tumbling, but the voltage was okay, and the telemetry looked good. But then we noticed some bad things like this. Our battery voltage was going down steadily, so we were thinking what happened, and it didn't take us too long to actually understand that we had a negative power budget. And the reason for that was actually the core reason for that is not yet identified by us, because we have only in telemetry from GomSpace CPS we have voltage for 3 different channels, but the current measurement is done by summing all of these. So the voltages appear okay for every axis, X, Y, and Z, but so there might be some hardware failure that might happen during launch, or I don't know, maybe due to radiation. So basically, we suspect that we don't get enough current from one of the axes of the sides of the solar panels. So EPS under voltage protection helped us to avoid critical failure, but the bad thing was that we put the FM beacon in the safe mode on. So actually, when the voltage dropped to 7.2, it's still, the beacon was operating. It was one of the most, actually the power consumption was too high for the beacon, and it was possible for it to even draw the battery more, and only when the battery dropped to 6.4 volts, the under voltage protection actually switched off all the outputs. So it was difficult to catch the time when the satellite was operational, and the reason for that was that we had also a problem with uplink budget. It appeared that probably due to deformation of antennas, we had really problems getting to the satellite. We needed to use about 100 watts of power, and we had a downlink and uplink instability due to tumbling and spinning. Also, what you have to take into account with the ISS orbit is that you have some periods of total night passes, so we had basically not to sleep to operate the satellite. But then we managed to get the satellite more or less steady, operational, and then the first success was the voice message of our president that was in the FM transponder as a identification message. So we believe this is the first woman president in the world to transmit a voice message. The successful transponder test, we got a lot of feedback, good feedback from radio amateurs. The signal was okay, just due to spinning of the satellite there was some fading, but general link was okay. We received more than 50 reports from all over the world, of course most of them from Europe and USA, and we also we are very grateful for amateur community, and we also got the Oscar designation for that. So just an example, what we learned is that if you have an amateur radio payload, it's really, the radio amateurs are very interested in your satellite, and you, for example, just by putting, I did this analysis by putting some very active amateurs who submitted data. So just by having these amateurs contribute to your mission, you can actually increase the coverage, total coverage of your satellite by 10-fold. So this is the first picture of our satellite. Due to some spherical aberration, we proved that the Earth is flat. But of course we got some more nice pictures that are more resembling the Earth. We also verified that the antennas are deployed. You see the two antennas here, and one is somewhere here. We found that although the resolution is low, you can basically use the land patterns to do the attitude verification. So in conclusions, we verified the cross camera operational in our satellite, a low-cost, low-resolution camera that we think might be useful for attitude and deployable verification for your mission. Also, we managed to achieve 1 image download per pass. That's quite okay. We proved the feasibility of FM transponder. We think ISS launch opportunity is very attractive for CubeSats in terms of accessibility, but you have to take into account that its orbital lifetime is very limited. Also, we think that until we have a fully functional CubeSat ground station network, the only way to increase your coverage is try to motivate the amateur radio community and justify the using of amateur frequencies by having some hand payload. And we strongly suggest not to use the protoflight philosophy that we used, because not only it's risky, but I would do everything that I could assemble again the satellite and to do troubleshooting. I think we would find the real causes of most of our problems with it. Unfortunately, the satellite now is unique, and we don't really have funds to build it again. So that would be our suggestions. And this is the plans for our next mission, the CubeSat 2, that is going to participate in QB50 projects. So since I don't have time, I'd be happy to discuss with you personally if you have questions. Thank you.
Thank you very much. Thanks for sharing these lessons learned. Any questions from the audience? I would have one. So there was, with respect to hardware failure being the reason for this power drain. And what kind of testing did you do?
We do individual testing with the solar panels, where we verified that the VI curves are okay, and we also did the operational testing that after connecting the solar panels to EPS that it is working, but we did not have the facilities to simulate the sun coming to the solar panels and to verify if the current is okay. So we can verify that the solar panels themselves produce the voltage and current, but we didn't check it after integration to the satellite.
You did the full mechanical test campaign, vibration, shock testing, thermal vacuum?
Yeah, we did these tests. We actually found, for those of you who are planning to use the pumpkin frame, be careful of one of the switch that has a lever. It tends to stick, just to get stuck in the path. But yeah, as I said, we didn't have capability to do solar panel test using Sun Simulator.
Thank you very much.